Hello and welcome to 4 questions which Corridor sent me. Basically, I think he wanted to keep me busy over the bank holiday. I'm actually quite thankful for it, because otherwise I'd be watching the telly and it's full of the royal coverage, and the rest of my family loves it, but I'm not so keen. Okay, so anyway, let's have a look. What have we got? He's sent me 9 questions actually, so yeah, plenty to keep me busy. But there's some really fun ones in there. I've only looked at the transformations so far because there was like different themes in there, and I thought I'd collect them together. Now, he must have sent me 4 questions on transformations, good questions as well, so thank you for that. We've got, and you might want to jump to different ones in this video, reflecting a line in a plane. That's what I'm going to do first. Reflecting a plane, transforming a plane essentially with a matrix to another plane. Yeah, and I think these two are very similar, so I'm going to do those first and point out the similarities. Number 9, transforming a circle with a 2x2 matrix. This was probably the toughest one, I thought, actually. And then finally, just using 3x3 matrices to work out different kind of aspects of transformations. Work out, for example, just write down a matrix representing a rotation, or basically work out different rotations. And there's definitely something I want to say about this, because the book gets this wrong and actually says the complete opposite of what you should do when you're rotating a point around the axes. It basically is absolutely incorrect, the description, a sentence it gives in the book. So I'd quite like to mention that. Anyway, let's start off with the first one. We're going to reflect a line in a plane. We've done this in class before, but it never hurts to do this again. Now, general strategy. We've got a line here, and I'm sure no one will be too fussed if I just immediately write it down in vector form. Let's write it down as 2, 4, minus 6, because the numbers on the top, if you change the signs, give you the point on the line, and then the direction is 4, minus 2, 1. Check it makes sense. Well, x would be 2 plus 4 lambda, so x minus 2 over 4 is lambda. Y would be 4 minus 2 lambda, so y minus 4 over minus 2 would be lambda, etc, etc. Yeah, it's looking good. Yeah, and then we've got this plane here. Now, what's my general strategy going to be? Well, I'm going to draw this out for you, because I do think drawing a decent diagram is massively important for getting these questions right. Basically, this is what we're trying to do. We've got a plane, and we've got a line. Let's say our line goes something like that. We don't know if it's perpendicular or not. Probably not, so I'm not going to draw it perpendicular. Ooh. So I'm going to draw it looking a bit wonky and doing something like that. Yeah, it's going through the plane. Yeah. Well, this is the line L1, and this is the plane P. And what the question's asking us to do is reflect this line in a plane. Now, when you reflect a line in a plane, one point which is invariant will be where the line meets the plane, because it's on the mirror, if you like, and therefore it's not going to be reflected. Every other point, though, well, the reflection will work something like this. Yeah. So I've drawn my original line. This will be the reflected line, and that's because the way this works is, let's say you have a point here. Yeah. Well, the way we're going to do it as well, in fact, what we're going to do is we're going to come up with the equation of a new line. Let's call this Ln, because this line is going to be normal, in the same direction as the normal to the plane. Yeah, and then what we're going to do with this new line is we're going to make sure that the distance from here to here is exactly the same as the distance from here down to here, and then that way it should lie on our reflected line. Let's call it LR. Yeah, and so here's the general strategy. Let's use lots of colour here and different dots. Basically, what we're going to do, we start off with L1 and the plane. We should be able to easily find a point where the line and the plane intersect. Let's call that P, and I'll do that not in red. Yeah, yeah. Okay, that's going to definitely lie on my reflection line. So I've got one point on my reflection line. But I need one more other point on my reflection line. Because really, if I've got to reflect a line in a plane, well then I've just got to reflect 2 points in that plane. Because the images of those 2 points will lie on my reflected line. Now the easy point to use is where the line intersects the plane, because that doesn't move, it's invariant. And then I can just find where this yellow one ends up. And it should be the same distance, shortest distance to the plane, double that distance, it should lie over here. And so the image of that reflected point will be down here. And so if this is, let's call it A, then this will be A dash, And P, well, P is going to equal P dash. In other words, P, when it gets reflected in the plane, doesn't move. And then once you've got 2 points, well, it's dead easy to find the vector or Cartesian equation of the line, the reflected line. So lots to do here, basically. Step 1, find the place where the line intersects the plane. And then step 2, find the equation for the line which is normal to the plane passing through A. Step 3, find where this line hits the plane so I can double that distance. And then step 4, find A dash, and step 5, find the line through A dash P dash. That's what we're going to do. And I've got a lovely picture of this on GeoGebra as well, which I'll show you once I've done it. So, okay, let's do it. Right, so step 1 was find P. Now, we've got this. Oh, I'll move it. It's nicer if you can just constantly see the diagram. So I'm just going to plug this into here. As you can see, x is 2 plus 4 lambda, y is 4 minus 2 lambda, z is minus 6 plus lambda. So I'm going to plug that in there. 2 plus 4 lambda minus 2 times 4 minus 2 lambda plus minus 6 plus lambda. Well, that equals 6. Quickly simplify this. That's not 12, it's a bracket. 4 lambda plus 4 lambda is 8 lambda. Plus a lambda is 9 lambda. Try not to hang about too much here. 2 minus 8 is minus 6. Minus another 6 is minus 12. But add it onto that 6, you're going to get 18. And so lambda equals 2 at the point P. Let's get rid of that equals P dash. And hence, if I just plug lambda equals 2 into this, I can now deduce the coordinates of P. And it's nice to write it on your drawn diagram because it's really helpful. 2 plus 2 times 4 is 10. 4 minus 2 times minus 2 is 0. And then minus 6 plus 2 is minus 4. So P should be at the point 10, 0, minus 4. Yeah? Okay, lovely. We've found P. We've got 1 point on our reflected line. That's really, really good. Now comes the more difficult bit. I'm going to find an equation for Lm. Now, it's actually each step, though, isn't really that difficult by itself. Now, if we want the equation for Lm, we need the direction of the line and we need a point on the line. Well, funnily enough, we've got that straight away because the point on the line is just simply A again. So A is a point 24 minus 6 in this example. Sorry, I should have written that down earlier. And the normal to the plane, well, that's the coefficients here, isn't it? Yeah? And so I can write that down as, now I'm going to have to use a different letter because I've already used lambda. Let's use mu, 1 minus 2, 1. And that's the equation of the line Ln. Yeah, let's just write Ln next to that to make it clear what it is on the diagram. Yeah, and now what I'm going to do is I'm going to find where Ln hits the plane. So same again, 2 plus mu minus 2 times 4 minus 2 mu plus minus 6 plus 1 mu. Oh, sorry, minus 1 times minus 6 plus mu. And that's supposed to equal 6 this time. Okay, mu plus 4 mu is 5 mu plus 1 is 6 mu. But this time you're going to have 2 plus 2 minus 8 is minus 6, minus 6 minus 12, add it on 18 again. So mu is 3. Now this is really important. We know that mu equals 0 when you're at A, because look at this equation. If mu is 0, you'd be at A. But if we want to get to the red dot, you can plug mu is 3 in here, by the way. And I'm going to call it C, actually, because I have on my GeoGebra, and I'll show you the GeoGebra version at the end. You could plug 3 in here, and you could work out C is 5 minus, what is that, 4 minus 6, which is minus 2, and then minus 6 plus 3, which is minus 3. So you can work out the coordinates of that, but it's not necessary, actually, because all we care about is if mu is 0 here and mu is 3 here, then at A dash mu is going to be 6. Because mu counts you up and down that line, like in equal amounts, basically multiples of this vector. And so A dash I can now write down. If I just sub in mu equals 6 into this equation, I can see that A dash is going to be 2 plus 6, 8. 4 minus 12 minus 8. And then lastly, minus 6 plus 6, that's 0. Yeah? And so that's it. I've found A dash. Now I've almost finished. They want the vector equation of the line, which is the reflected line. Well, that's this line here. A dash lies on it, P lies on it, so I can now do it. So what are they calling it? What do they label it? L2, yeah? So I can say, hence, L2 is going to be given by, well, r equals 10, 0, minus 4 plus, let's say, t times, because we've already used lambda and mu, and then we need like minus 2 if you like, doesn't matter which way around you go here, minus 8, and then minus 4 to 0 is 4. And obviously we could cancel that down, etc, etc. So there we go, that's how we do it. Did they want a vector equation of a line L2? Yeah, good, they didn't ask for Cartesian. Just to quickly show you what this looks like, I will just quickly show you this on GeoGebra because it's nice. Okay, I've drawn the plane here, yeah, and that is the original line. The red line is the original line, and what I'm arguing for in this method is that if you take the original line, you can find where it hits the plane, yeah, and this is because, let me show you the reflected line actually. There's the reflected line, yeah. If you take the original line, which is the red line, find where it meets the plane, you've got 1 point on the reflected line. But then find a line, this is the dotted line in my diagram, which goes through the point A but is also perpendicular to the plane. And can you see that's at right angles to the plane? I hope you can, yeah. Okay, so find the line through the point A, which is perpendicular to the plane, find where it hits here, make sure that's equidistant to there, that's A dash, and then sure enough, you've got 2 points, so you can find the equation of a reflected line. By the way, the nice thing about GeoGebra here was it gave me a lovely way of checking my answers. You know what it's like when you're using Mad as Maths or these other websites, they do occasionally have mistakes, not often, but they do occasionally, where you can check things. Look at this. Type in a plane, put a point there, yeah. I like literally if I just take everything else off, not A though. Where's A? Let me put A back on there. I'd want to leave the plane on as well. So if I just have everything else off, and I just had this point, I don't even need the point P on there. I don't know why it's stayed on there. That's weird. Oh, what happened there? Let me just go. Okay, right. Okay, what I'm saying is I can actually reflect the point in the plane and check my answer, because look at this. I just click this and click the plane. Oh, have I already done it? Sorry, reflecting the plane. There we go, and it's reflected it, and you'll see that that is 8 minus 8, 0. So yeah, I can easily check answers on this. It draws straight lines in 3D as well and everything else. It never used to that easily, but now it's really easy, GeoGebra, to draw straight lines in 3D and stuff like that. So you can easily just select this actually, and you can see when your answers are right. So lovely way of checking your answer. Oh, I shouldn't have done line segment, I should have just done line. There we go, you know, and then I can easily check that, and does it look right? It looks like a reflection. Yeah, sure enough it does. Ooh, I'm going crazy. Anyway, so there we go. So that's the first question. I hope that makes sense now, how to reflect a line in a plane. It's quite good fun, that one. I don't mind it at all. Okay, this one's quite interesting. James asked me about this actually, and asked me why a certain method failed, which is a very interesting misconception which I wasn't aware of, but very interesting, that the normal is not necessarily well behaved under a transformation. It's what I describe as well behaved, as in it doesn't necessarily transform like all the points. But anyway, I want to show you the easy way of doing this one. If you want to take a plane and transform it using a matrix, there's a couple of ways you can do it. You could just take this matrix and times it by the general point on this plane, which would be like 1 plus 2 lambda plus mu, 2 plus lambda, and 1 plus 2 mu. Times that by that general point and end up with a different general point. That will be your plane after it's been transformed, etc, etc. But there's actually an easier way. If you're transforming a plane, this is a bit like what I just did above. If you're reflecting a line, well, why not just reflect a couple of points? Yeah. Well, this is a similar thing. If you're transforming a plane, rather than transforming the whole plane, why don't we just transform 3 points and see where they end up after the transformation? And then I can just find the equation of the plane through those 3 points. So that's what I'm going to do. Clearly, a point on this is 1, 2, 1. But I could also set lambda equal to 1 and mu equal to 0 and come up with another point for B. Yeah, so this is lambda equals 0, mu equals 0, this first one, isn't it? Well, if I said lambda equals 1, mu equals 0, then I've got 3, 3, 1. Yeah, but I could have done it the other way around. I could have said lambda is 0, mu is 1, and I could have done it, you know, obviously I can pick any lambda and mu values to generate these 3 points, but this seemed like the most obvious way of doing it. Then we're going to get 1, what's that, 1 plus 0 plus 1 is 2. And then we're going to have 2 plus 0 plus 0, so that's 2. And then you're going to have 1 plus 0 plus 2, which is 3. Yeah, okay, we've got 3 points, and now I'm just going to transform them using this matrix. So what I'm going to do is I'm going to take 1, 1, 1, 0, 1, 2, 2, 0, 1, and I'm going to multiply it by. Now you could write each one down individually, but it's just as easy to write another 3 by 3 matrix down, 1, 2, 1, 3, 3, 1, and 2, 2, 3, and find out where these points go. Yeah, because this will obviously show us where these points end up after we've, performed the transformation. You should be post multiplying by the points as well, just like we normally do. Normally we have a matrix times x, y, z equals, say, a, b, c. Do you know what I mean? Like, in other words, we transform a point by pre-multiplying by the transformation matrix. Okay, so that's important, that. Okay, so I'm doing that. I end up with, now, I messed this up because it was early in the morning and I was, as always, not using a calculator because it's far away or in the shed or wherever, and it just means, I mean, I need to use a calculator because I keep making mistakes, but it just means that when I check my answer at the end, it ended up wrong, and it shows the importance of checking your answer at the end. But anyway, I times that by that, and I see that A, B and C end up as A dash, B dash and C dash. So, these are written as column vectors, the transformed points. Okay, so I know that my plane actually includes these 3 points. Well, now all I've got to do is just find the equation of a plane through 3 points, which I feel very comfortable doing. Yeah, and C dash is 8, 4, 9. So all I'm going to do is I'm just going to do it the standard way. I need to find a vector which is perpendicular to 2 vectors in this plane. So if I think of A dash, B dash, that's going to be 3 to 5 is 2, 3 to 6 is 3, 6 to 10 is 4. So I've got 2, 3, 4 for that. I went wrong here as well earlier when I did this in the kitchen. Clearly I needed another coffee. The good news is, because I always check my answers, because I don't want to look too silly, I managed to spot it. Yeah, and this comes to 5, 1, 3, because at 5, 1, and 3. And okay, now I'm just going to find A dash, B dash crossed with A dash, C dash. Yeah. And that we do by the normal way, IJK, 2, 3, 4, 5, 1, 3. And we just multiply it out in the normal way. Okay, so I'm working out the I1 first. 9 minus 4 is 5. When I'm doing the J1, I normally remind myself by putting a minus there, and I do 6 minus 20, which is minus 14, but that's going to become plus 14. And then lastly, I'm going to do the K2, minus 15 is minus 13. Okay, what does this represent? It represents the normal to our plane. And so we know it's definitely of the form 5x plus 14y minus 13z equals d. Now what we can do to find d is plug in any point we like on the plane. I'm going to use A dash just because it's there. A dash was 336. And we'll work out d. So if we plug this in, I could just say by inspection here, because I'm going to do the next bit in my head, which is a bit dangerous. 15 plus 42 is 57, but then I'm taking away 13 times 6, which is 78. And now I've forgotten what I said. 15 plus 42 is 57, minus 78, I think, is minus 21. And so d equals minus 21. And therefore I get 5x plus 14y minus 13z equals minus 21. Now, a couple of points about checking your answer. Like, if you've got time in the exam, and it literally takes seconds on a calculator, plug in B or C, check it definitely lies on the plane. That establishes that you've definitely found the right plane through A dash, B dash, C dash. You don't need the answers or mark scheme to check that. But if you want to check that you've definitely done the whole question right, set another value for lambda and mu here. I think I did lambda equals 1, mu equals 1, and I found a new point D, and that obviously that D is 433. If you've got lambda is 1, mu is 1 there, and then I very quickly transformed it with this matrix. So I did like 1, 0, 2. Oh, I can't see it now. I like showing you how I check my answers, because remember, in the exam, checking your answers, like, I mean, as long as it doesn't take too long, it should be well worth doing, because then you can just leave that question alone once you know you've got it right. Okay, so I'm just going to transform that point. You can do that on a calculator very quick. You get 10, 7, 13. And then I just checked that this point, because this is like D and D dash, isn't it? D and D dash, I checked that D dash was on my plane as well, because that was nothing to do with my working out here. And sure enough, if you do 5 times 10, which is 50, plus 4 times 7, which is 98, minus 13 times 13, which is 169, that's 148 minus 169, which is also minus 21, so D dash lies on plane as well. And that's why I know I've done that whole question correctly. Okay, right, so that's that one done. Right, question 9. This was probably the most fun I had this morning because it was genuinely hard. Yeah, like the other two I didn't mind so much, but this one, I've never seen one like this in the exam, but I'd love to see it, and I don't see why. I wouldn't like to say it definitely can't come up. I'd say it's very unlikely, but you know what my predictions are like. If I say it's very unlikely, it will be question 1. So, you know, like bear that in mind. First thing I'm going to point out here is when I'm transforming by a matrix, what I normally like to do is times it by x, and then I'm going to write in y here, but in terms of x. So y is clearly going to be square root of 4 minus x squared here. Technically you should have a plus or minus here, but you know, let's not worry about that too much at the moment. Maybe we'll discuss that at the end, yeah? I'm just going to put y equals square root of 4 minus x squared. Okay, so I'll put square root of 4 minus x squared in here. Yeah. Okay, right. And I'm just going to do that times that. And what's it going to give me? Well, 2 times x plus 3 times that, I get 2x plus 3 times root 4 minus x squared. And then I get 2x plus 4 times root 4 minus x squared. Yeah. Now be really careful here. Yeah. Remember that this is your transformed point. So use different letters. I'm going to use capital X and capital Y. So capital X, which or you can use X dash as well because it means the same thing. It's a transformed point. Capital X is 2x plus 3 root 4 minus x squared. And capital Y is 2x plus 4 root 4 minus x squared, yeah? And this looks awful. It really does. What is it? What are we really dealing with here? This is a parametric problem, yeah? Like, the reason it's parametric problem, just replace curly x with t, yeah? Can you see then that I've got x in terms of a parameter t and y in terms of a parameter t? We're basically defining new x and new y in terms of the old x coordinate, yeah? And so it's a parametric equation problem. Now, parametric equations, when you're going from parametric to Cartesian, it's difficult, yeah, and it feels like a bag of tricks, and sometimes you need some real kind of like imagination and creativity to try and find the Cartesian form. You really do. It's a tough part of maths, it really is, and it's definitely something where you need kind of like creativity. That's why I quite like it though. That's why it's a fun question. So it's like, how are we going to eliminate curly x here? How are we going to eliminate it? Well, you know, this definitely was the toughest one for me. It got my head scratching and stuff like that. First thing I thought was, well, that's very similar to that. In fact, I could say that y take away x is just, well, 2x minus 2x is nothing. 4 root 4 minus x squared minus 3 root 4 minus x squared just leaves 1 root 4 minus curly x squared, yeah? And I thought, okay, haven't eliminated the parameter, but I've at least made it a bit nicer. And I thought to myself, well, if only I could rewrite the, you know, y and x in terms of root 4 minus x squared in another way. Yeah, and that's what I started to think about doing. Now, it wasn't an instant solution. It took me a little while thinking. If we call this one A and this one B, what I then did was I thought, well, okay, hang on a second. I could say that x take away 2 curly x over 3. Well, that's root 4 minus x squared. And similarly, y minus 2x over 4 is root 4 minus x squared, yeah? That was my kind of thinking here, yeah? And now what I can do is I can like have another way of expressing this, like, so what I can do is I can times by the 4, you know, it might not look that, you know, that good at first, but what I guess I'm thinking here is, let me make my thinking a bit clearer, because basically with these two I reckon I can do it, because here's my thinking. Can I make this curly x equals? Yes, I can. Can I make this curly x equals? Yes, I can. Am I really writing down the same equation in both? No, I'm not, yeah? So let's call this one star and this one diamond. Looking at star, I can say that y minus x, capitals squared, well, that's going to be equal to 4 minus x squared. Yeah, that's kind of nice. Now let's look at diamond, because I think diamond I'll have a bit more luck to making curly x a subject. I can say 4 capital X minus 8 little x equals 3 capital Y minus 6 little x. Yeah, and then I can group the x's together. So I can get 4 capital X minus 3 capital Y is going to be 2x. Lovely, lovely, yeah? Because now I can make this baby x equals, so I can have 4 capital X minus 3y over 2 equals baby x. Now I can plug that in there, and I've got rid of my parameter. I've done it, I've done it. Now, y minus x, capital X, that is all squared, equals 4. Take away 4x minus 3y over 2 all squared, yeah? So y minus x all squared plus 4x minus 3y over 2 all squared equals 4. Times it all by 4, because that's going to square to 4, and you get, I think this, you know, I didn't bother I could have times it out after this as well and collected the x squareds together, but I didn't bother. I quite liked it in this form, to be honest, because it looked like what I'd figured out as well was that we were going to end up with what looked like a wonky ellipse, yeah? And the reason why I figured that out is, once again, I actually took a few points on this circle and plugged it into this matrix, and I realised things like, yeah, clearly it's a circle centre, you know, radius 2, centre 0, 0. I realised that the point 0, 2, for example, well, if you times this by 0, 2, you actually end up with 6, 8, yeah? And I did a couple more points. I also did 2, 0, and that one went to 4, 4, I think. And I started realising this is going to turn a circle into like a weird squashed ellipse. And that's exactly what it does. Let me show you on GeoGebra. You know, I love getting out the GeoGebra, any excuse. Okay, let's get a new bit of GeoGebra on. Don't save. It's all the same. Go off of 3D, just a normal graphing. Okay, so if I type in x squared plus y squared equals 4, just so we see the original circle. It's quite a nice question, this, as in, like, I haven't seen one like this, and I like it. Yeah. So now let's type in that weird one we found. 4 times by 4 times by y take away x all squared plus 4x minus 3y all squared equals 16. Now, I'm not saying this is a perfect way of checking your answer. Look at that. It's cool, isn't it? That is basically how we, what we end up with. Kind of cool transformation. It reminded me a lot of a topic called complex transformations in the plane, which used to be in a course. Now, if you look, 6, 8 lies on the curve, so it's looking good. You know, this is just a way of checking your answer casually with GeoGebra. Like, it's looking good, basically. That looks like correct to me. But do let me know if the mark scheme said something different. It's probably equivalent to mine if it said something different. I don't know where any of the answers are to these things. They look like maybe mad as maths questions or other questions you've found on past papers or whatever. Doesn't really matter, does it, where they come from? Let's just make sure we can do them all. Okay, so that's that one. Okay, the last one, last transformation of this morning. Okay, what have we got here? This is basically a question which you can do well if you are really familiar with the idea of, you remember in 2x2 matrices where I might have written down something like this and said, what's the transformation? Yeah, and what I hope you do is you think, well, the identity matrix looks like 1, 0, 0, 1, where the first column can be thought of as this point and the second column as this point, and then just think, right, if this is going to this, what happens to these 2 points? Well, this one stays the same, and this one's going down here to become negative, so that would represent a reflection in the x-axis, yeah? That technique is all this question requires, but just in 3 dimensions. So let's do it. What do we got first? Right, first things first, we've got to describe what this transformation is. Well, I tell you what I'm going to do here. I think I actually copied it over. This is just because my drawing isn't brilliant on the graphics tablet, but on pen and paper it's not that bad. But I'm going to use this little, it will look much neater if I actually use this 3D drawing of what's going on. Yeah, so we're thinking about where basically the identity matrix, which has in order columns 1 0 0 0 1 0 0 0 1, so that's the identity. You can think of that as point A, point B and point C on my diagram, because the red axis is X, green is Y, blue is Z. Right, where is the X1 ending up? Well, it's actually ending up here on the Z-axis. Yeah, so okay, that's fine. That's a little hint about what's going on. What's happening with B? B's staying where it is. B is invariant. Oh, very interesting. B isn't moving at all. And then finally C, where's C going? C is going over here to negative 1 0 0. Yeah, in other words, it's going to go there. Now, what type of transformation is that? Well, clearly it's a rotation about Y, because that's why the Y-axis point is invariant. And it's 90 degrees. Now, here's the big question. Is it clockwise or anti-clockwise? Well, this is where there's a mistake in the book. The book actually says, and I quote, on page 145 of the AS textbook, in all cases, theta is the angle measured anti-clockwise where facing the positive direction. I think that's wrong. I think it's theta is the angle measured anti-clockwise when facing standing on the positive side facing the negative direction. Basically all of these are done standing on the positive side facing the origin. Yeah, and I'm pretty sure that's a mistake in the textbook. We can talk through it and argue about which way we're going for clockwise to anti-clockwise. It's not that big a deal really, as long as we all just stick to the same convention. But like I think the convention is to stand on the positive side and face 0. So if you were looking here, if this is where your eyes were, I'm going to show you my brilliant art. There we go. Yeah, if that's where your eyeballs are, well, you know, currently it looks like you're turning anti-clockwise, and therefore if you go on the other side and look at it, it will be turning clockwise. So I think that's clockwise. Yeah. Let me know what the mark scheme says and if it agrees with me, because I'd love to hear it. If it doesn't, it always makes me chuckle. Okay. Part B, the 3x3 matrix represents a rotation of 180 degrees about the line x equals z. Now, this is interesting, because if they didn't include this last bit here, I'd be like, that's not a line, that's a plane. But no, they have to give it an extra condition to turn it into a line, and y equals 0. Okay, so what does this look like? Well, if you don't mind, I'm just going to rub out all the other stuff I had on the diagram so I can draw this thing. Yeah, so y equals 0 firstly means that I'm not varying the y-axis. Yeah, it means I'm lying in the plane which the z-axis and x-axis lie in. Yeah, I'm not got any depth to this, if you see what I mean. Yeah, because y is 0. Yeah, but then I've also on the line x equals z, so it's going to be the line which kind of comes up like that, you know, where 1 1 is, 2 2 is, 3 3 is, 4 4 is. I hope I've drawn it correctly. It almost looks like exactly like where the y-axis is, which is unfortunate, but it's not the y-axis, it's a line coming across that plane like that, where x equals z. Yeah, and it's hard to imagine these. It's really, you know, it's all about your diagram. I can show you on GeoGebra at the end, and use GeoGebra to get a better understanding of the 3D world. I messed up a 3D trig question the other day in a Year 11 paper, you know, because it's hard to do 3D thinking. It really is, to twist your mind round to it, finding an angle between a line and a plane. It's not easy. Okay, but what are we doing here? So we're going to try and represent this, yeah, and we're going to do it just the same way as before. We're going to think about where x, y and z end up. Yeah, now if you're rotating about the line x equals z when y is 0, yeah, well, okay, fine, we'll try and rotate about that. What's going to happen to these points? Well, if you're rotating this one about this line, should be ending up rotating 180 degrees. It's basically a reflection, so this one's going to end up over here at -1. Let me do these in different colours, or I'll label it quite clearly actually. So this is B dash, yeah, which is the green one here. A is going to be reflected onto C, and C is going to be reflected onto A, because a rotation of 180 degrees is just like a reflection basically. And so this is now C dash, and this is now A dash. And so I think it should be, okay, so where has A gone? A's gone to where C was, and so it's 0 0 1. Where has B gone? It's gone to the negative of what it was before, so that's minus 1, 0. And where's C gone? It's now gone to where A is, so 1, 0, 0. And there we go. I think that is matrix B. Yeah? Okay, for the last bit, what we got to do, I'm just going to rub that out, that's kind of in my way. We've got C by 3 by 3 matrix. C is a transformation B followed by transformation A. Now remember, if you're doing B first, then A, read from right to left, yeah? So I'm going to do A times by B, which is, let me just remind myself what A is. Right, okay, because I'm going to times them together first, and then I'm going to suss out what kind of transformation that is. So 0, 1, 0, minus 1, 0, 0, and I'm going to multiply that by 0, 0, 1, 0 minus 1, 0, 1, 0, 0. Obviously in exam you'd do this on a calculator. I'm going to quickly do it in my head. 0, 0, minus 1, and then 0, 0, 0, and then 0, 0, 0, and then 0, 0, 0. Sorry about this, a lot of zeros. 0, minus 1, 0, and then 0, 0, 0, and then lastly 0, 0, 0. Sorry, 0, 0, 0, and then what's this last one? 1, 0, 0. Yeah, so I think it comes to minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. Now, what kind of transformation is that? Well, if we just rub all this out again, we can figure out what this is doing. Let's do it. It's good for you, this question, definitely. I'd love something like this to come up. It will really show who's good at the geometric thinking and drawing a decent diagram. Okay, so by the look of it, A goes to minus A. Well, you know, minus 1, sorry. There's A dash. B goes over here. That's interesting. And C is invariant, doesn't move. Well, what is that? That looks like a rotation of 180 degrees about the z-axis. I've written down 90 degrees here, that's clearly wrong. This is a rotation of 180 degrees about the z-axis. That's why z is invariant there. Yeah, I don't know why I've put, yeah, I've definitely got that wrong. So I don't need to put clockwise or anti-clockwise because it will work the same either way. Okay, let me know if I've made a mistake or anything like that. Those were my answers. Let me know in the comments. Humiliate me in class or whatever. We've only got, what, 4 days? No, a week left. Well, 4 days because it's a long weekend. But, so yeah, now's the time to talk to me and let me know how we're getting on. Well done, though. Keep up the hard work. You're all working really hard on this and you're finding me some terrifyingly difficult questions, which is good. That's good. You know, hope for the best, but prepare for the worst. Right, keep it up. Bye-bye.